Okay, so from data to batteries and data, we're gonna go straight into our little startup that's 9 plus a few more now. Wonderful people on the other side of the river trying to solve circularity around batteries. And I'm going to try to be a bit quick through the business parts to be able to maybe bring some software to the software days here as well. But the long-term goal is, of course, to be able to reuse and more efficiently use batteries that are already out here. Because, of course, we will have some future batteries, but today we already have batteries, but we're not using them efficiently enough. And to kind of kick up and start the focus of what we're usually talking about, we have this picture, which we love. And imagine that you have a banana. You go and buy a banana, you have it in front of you, and then you just maybe open it, but then you take a bite out of it, and you take 90% of the banana and throw it away. That's usually how many batteries are being used today. And of course, in some advanced examples, you have a Tesla that doesn't go all the way to Stockholm. You want a new Tesla or a new battery in that, down to like your robotic vacuum cleaner that someone bought. It's somewhere in the apartment. It has almost not been used, but there's still batteries in there that you just throw away. And of course, the bigger the vehicles, the more vehicles we're looking into, the more that waste becomes. And to kind of take our first bit technical depth here, we're looking at a state of health degradation curve over time. So state of health is pretty much how happy is the battery, how well is the battery feeling, and it can be translated to how much energy can you get out of the battery. And of course, as most of you know, if you pretend that you're on 40% of like how many percent battery you have left, the state of charge, you know that a new iPhone is not 40% in a new iPhone is not the same as 40% in a 3-year-old iPhone. I think everyone has related to that in some way, but of course it's the same thing with every vehicle, every power storage, every item, electrified item that we have. And unfortunately today, somewhere around 50 to 80%, depending on the application, when the state of health is 50 to 80%, we simply throw that item away. We throw the battery away, we want a new battery. In some good cases, most here in Europe, we recycle the batteries. On a global scale, unfortunately, there's a lot of landfills still. So what we want to do, the short version, is that we want to move our battery that isn't good enough for the high performance need. It is not good enough to launch a new Volvo car fast enough to Stockholm, but it might still be good enough to use, for instance, in a power storage connected to a solar power plant or connected to a wind power plant. And simply be able to extend the life of that. And that's what we see here on the curve. We see a first life in black and then a second life in green, with lower need for performance. So we could move this battery from the first to the second life in some way. And of course, this is what everyone that works with batteries want to do in some way, but the big blocker for doing this today is that we don't know so much about how batteries degrade, and especially not in the first generation of vehicles that we have that might be old enough to recycle now. Because as you know, an old car, if you go to a, a diesel car, for instance, then you will have a mileage. If it goes 100,000 kilometers, it's ish old, and you would put this second-hand price on it. But when you talk about batteries, there's so much more complexity going into how batteries degrade. And I'm going to just jump straight over that, because that's another lecture. And simply focus on what happens with that. So let's say that you have, and you want to buy a second-hand Tesla. The problem is that you don't know how it's been driven. Of course, a good point would be don't buy an electric car with a spoiler on it, because then it's probably been driven pretty fast, and that's not good for the battery. And be able to say, like, how much should I pay for this electric car is, of course, depending on how good it is. And that's a very good consumer perspective to thinking about batteries and degradation, like how much should I pay for a second-hand car? But the interesting thing becomes when you, like Björn talked about here before, had fleets of vehicles. Let's say you're a power company wanting to buy 10,000 batteries, 10,000 car batteries to put inside a power storage next to a wind power plant, for instance. You don't want to buy, as we love the Swedish expression, the pig in the bag, and just get a random battery. You want to get batteries that you know will be able to perform in these new applications, because you pretty much fund a big construction project and buy the batteries. You want to know that they are good enough to be used. And this is what we're focusing on. And I think, like we said, most companies are looking into this in some way. It's very common to do lab testing, where you take in every battery to do a test in the lab and get a pretty accurate picture of how each individual battery performs. But that's an expensive process. So what we're trying to do instead is to gather data from the batteries while they're out, while they're being used, while they're being driven around, and kind of take that insights back into a cloud to provide analysis back to the systems. And to compare this with what Björn was talking about, you were talking about the BMS, the computer inside the battery. We're talking about the computer outside the battery, or what we can move into the cloud, or BMS plus, or offboarding from BMS. And of course, batteries are complex. But what we've kind of seen the industry been moving towards is some kind of digital twin, or a digital representation of batteries. So every time I drive my car to Stockholm, then the digital car or the digital battery will change in some way. And we combine three different kind of aspects to this. One of them is the physical-based modeling, which is mostly based in the best practice from academia to some of our friends here in Chalmers at Uppsala, to some international universities, to kind of see where do we go to kind of accurately predict how the chemical cell degradation will change. On the other side, we add an empirical level of statistical analysis that we bring into this analysis. And here's where the kind of AI or the self-recursive algorithms come in to learn from these different models and see from different data sets how that changes over time. Because of course, like if we talk to a large car company, we will not be better than that car company at anticipating how good the battery is in that car. But the interesting point is to see what happens in the network. What happens to a car battery when it's no longer in a car, when it's in a solar power storage, for instance? What happens when you move between different solutions? What happens if you develop batteries for e-scooters or for trucks on the same way that you have developed for cars? You somehow need intelligence into these network effects. And to kind of go back to the effect of it, is pretty much the focus that we have has been on like finding when this exponential degradation comes. Because battery degradation is advanced, it's another lecture, but to summarize it from a statistical perspective, you kind of have a pretty, like a graph looking like this, that after some time you will have some kind of exponential degradation if you continue using the battery in the same way. And finding out when that happens is the kind of holy grail of battery analytics. We try to do that. Tesla tries to do that. Everyone tries to do that. No one is that close. There might be some rough indications, but this is what everyone wants to get in the future, to know exactly when a battery is not good enough anymore. But the same insights that we develop to understand when a battery is not good enough is insights that we can use in the first life. For instance, how charging compares to battery. Like how many times has the battery been, fast charged in very cold weather? How many times have the car been driven insanely fast? All these kind of flags and markers is intelligence that we can bring into the system to prevent it, both telling our users and our fleet customers like what behavior they should not go into, but also for valuing batteries later, see how has it been done during the way. And by knowing these things, like trying to understand how batteries age over time, we can prevent that, making battery lives last longer, and of course, bringing efficiency to the batteries themselves. And again, back to the cell phones, you've all read some tips about like charge it slower because that makes the battery last longer. That's like a general good tip, but it's much more complex than that. So kind of bringing those intelligence points back into the system is what we're trying to do in order to kind of promote that efficiency even in the first life as a cloud addition to the BMS system. And to kind of go over, go from problem to solution to the problem with the solution, is that, as you might all know, looking into AI or any kind of modeling on data, the problem is data. And of course, first you want data, then you want to realize what data, you need to sort that data, and you need to understand like the cost of calculating on the data. So here's a chart that we got from the Research Institutes of Sweden, looking into us specifically, looking at what kind of data do we want to have. The blue dots or the blue arrows are what might be available today. The red ones are what could be available tomorrow. And of course, we want to save efficiency on batteries. We want to save money on batteries. And in that effect, kind of give a better sustainability effect, like lessen the environmental impact of the battery use. But if we get too much data, especially if we do it unintelligent, there is a big risk that the cost of the analysis will become bigger than the battery degradation itself. Because if we maximize what we can get out of an e-scooter, we're talking about many tens of gigabytes per day per scooter, and that's only looking at the BMS. We're not even talking about the fleet systems and the different actors in the supply chain. So if we look at the complete data availability, including maybe from weather sites externally, we're talking about many hundreds of gigabytes per battery per day, and that's not anywhere near computationally possible today. Hopefully with some 6G we might increase what's feasible, but it's still a long way left. So what we think is one of the biggest competitive assumption that we have to work with, as like all analytics companies have to work with regardless of the field, is to kind of figure out ways to minimize the data need for the computations that we need to do. And then we have like a lot of interesting perspectives of how this can be done. We're talking about, instead of having like time series data all over in high resolution, we can get mathematical functions to kind of fit on that scale in every step, so to say. But we're also talking about, instead of collecting all the data from every battery at every time, that we might be able to look into some batteries with more data and then take snapshots of the rest of them. Because if we think back to this old curve, maybe I can even use the back button here. If we know what patterns give this curve, then just getting like a small piece of the curve, we might be able to fit in a new battery to where we believe it is. To kind of find these intelligent decisions is needed if in the future you want to do quick testing of second-hand batteries or be able to use snapshot data instead of having complete histories, which we need today to make accurate predictions. I think I'm going to put a line there, or draw a line there early.